Lamp black, or carbon black, is a material which is produced via incomplete combustion which deposits onto surfaces in proximity to a flame, similar to soot. Due to its intense color, or lack thereof, lamp black has been used for thousands of years as a pigment for inks and paints, and continues to serve this purpose to this day, used in printer toners, polymer pigment, paints, etc. The creation of lamp black follows a very simple procedure. Ignite a flame fueled by oil or wax, and hold an object barely within the flame. For this demo, we will need a candle, a lighter, the material you wish to deposit the lamp black onto, and pliers or tongs. As mentioned previously, all we need to do is ignite the candle and hold our material only slightly above or even within the flame. The longer the object is held near the flame, the thicker the deposition will be. The difference in film thickness can be observed here. As the glass slide is moved up and down, the candle flame is completely obscured by thick deposits and simply dimmed by thin deposits. Unfortunately, the adhesion of this film is very poor, so it would have to be stabilized with an adhesive or epoxy. Alternatively, it can be removed completely, mixed into a paint or other application media, and reapplied. The burning of a candle is, in a simplified form, the combustion of a hydrocarbon into carbon dioxide, water, carbon monoxide, and carbon, where the balance of the products is determined by the extent of combustion. Assuming that complete combustion occurs, carbon dioxide and water are released in their gaseous form, but if there were a change to the availability of oxygen, particularly one where the supply of oxygen was diminished, some extent of incomplete combustion occurs, resulting in the additional formation of carbon monoxide and carbon as a gas and as a fine particulate respectively. In this demo, when we place a substrate in the path of the flame, oxygen is limited where the flame and the substrate meet, resulting in incomplete combustion, which produces carbon that is deposited onto the substrate. Interestingly, if we were to dissect the candle flame, we would be able to see that the flame itself is hollow, and that only the outermost region of the flame is supplied with enough oxygen to sustain combustion. We can also see this by quickly introducing and removing the substrate, where we find the carbon is deposited in a ring. In this demo, we explored how a simple candle could be used to create a thin film of fine carbon particles on a substrate, where the processing time affects the deposition thickness, and the hollow nature of the flame affects the uniformity of the deposition. Spin coating is a technique used to deposit uniform thin films onto a substrate by means of high-speed rotation. The process begins by applying a small amount of the coating media to the center of the substrate. The substrate is then spun quickly, allowing centrifugal force to disperse the coating media to coat the substrate evenly, where any excess is simply ejected off the edge of the substrate. Rotating the substrate at a higher speed and/or for a longer period of time can produce a thinner film. Additionally, many properties such as the coating viscosity can be manipulated to affect the final thickness of the thin film. Due to its simplicity and reliability, spin coating is implemented in a wide array of engineering applications, including microfabrication of functional oxide layers, photolithography, and the fabrication of planar photonic structures, all of which have use in energy and information technologies. For this demo, we will need acrylic paint or nail polish, 50% rubbing alcohol, small mixing containers, wires, preferably with alligator clips, a hobby motor. This one here is a Type 130 micromotor, a variable DC power supply, though a battery will work. Type 130 motors typically require 1 to 4.5 volts to operate. Microscope slides, though any rigid flat surface should suffice, a medium container to house the spinner. 3D printed mounting fixtures are used here, though strong glue would also work. Painter's tape is optional. The motor is inserted into the mounting fixture and secured into the center of the housing container. A microscope slide is placed onto the mounting fixture. Painter's tape is used here to provide a barrier from the coating, resulting in a clean area with which the slide can later be handled. A few drops of paint or nail polish are placed onto the center of the slide. For the purposes of this demo, the exact amount of paint should not have significant effect on film thickness as the excess will be flung off the slide. The lid of the container is secured, and the motor is connected to the power supply and allowed to run at roughly 2000 RPM for approximately 25 seconds. After the time has elapsed, the motor is disconnected from the power supply and the slide is removed. 2 more paint mixtures were prepared at a 1:1 and a 1:2 ratio of paint to rubbing alcohol. The experiment is repeated with the prepared mixtures. Comparing the 3 samples, the 1:0 sample appears to be the thickest, followed by the 1:1 and 1:2, based on the translucency of each film. When placed on a patterned surface, The pattern is shown through the 1 to 2 sample the most, barely registers on the 1 to 1, and is completely obscured by the 1 to 0. In this demo, we explored how the viscosity of the coating media affects the thickness of a spun coating. A higher viscosity media will resist the flow induced by rotation, resulting in a thicker film. Another avenue worth exploring is the operating time or rotation speed. Allowing the procedure to operate for a longer period of time will allow the media more time to flow and self-thin, provided the media itself does not set into a stable deposition. Increasing the rotation speed would assist in the thinning of the film. Electroplating, also known as electrodeposition, is a process by which a conductive surface is coated in a thin film of alternate material in order to alter properties ranging from corrosion or wear resistance to aesthetic appeal. Common applications of this technique include chromium plating to improve corrosion resistance in automotive applications or the plating of inexpensive jewelry with precious metals to increase their value. Electroplating is comprised of 4 general elements: the object to be coated, acting as the cathode, the plating material, acting as the anode, the electrolytic bath in which both electrodes will be submerged, and a power source, all of which form a circuit. An electric potential is applied across the circuit, promoting oxidation at the anode, which introduces cations into the solution, where the cations are eventually reduced at the cathode, to which they deposit. In this demo, copper will be oxidized at the anode and undergo the following reaction. Copper solid goes to copper 2+ ions and 2 electrons. The ions will then undergo the reverse reaction at the cathode when they are reduced, forming a solid film. For this demo we will need a jar, table salt, vinegar, copper scraps, a low amperage power supply, less than 1 amp. 1.5 volt batteries also work well. Wires, preferably with alligator clips, and a nickel object for plating. The first step in creating our electroplating cell is to create a solution with dissolved copper ions. While it would be easy to simply add some copper sulfate to water, there is another approach that we can take. Firstly, our jar is filled with vinegar and a pinch or 2 of salt to improve the conductivity of the solution. A wound section of bare copper wire, which will act as our anode, and a sheet of copper, which will act as our cathode, are lowered into the jar and connected to the power supply, ensuring they do not touch. At this point, we will have noticed bubbles emanating from the electrodes. One should be producing a great deal more bubbles than the other. In the event that we are not certain which scrap is the cathode or anode, we can use this opportunity to assess that there is hydrogen evolution occurring at the cathode. We will need to remember which scrap is the cathode. This setup will be left for about 2 hours or until the solution takes on a blue tinge, which indicates dissolved copper in the solution. When our solution is ready, we can disconnect the power supply. The cathode is retrieved and replaced with the object to be plated, which is then lowered back into the solution, ensuring that the part and the copper anode do not touch. The power supply is then reconnected and left until the desired coating thickness or appearance is attained. Here we can see the difference between an unplated and a plated quarter. Looking closely, there is some splotching on the coating, which is likely caused by the purity of the scrap used. In this demo, we explored how a metal is deposited onto a conductive surface via electrodeposition. This technique provides films with great adhesion and uniformity. Further avenues for investigation may include stirring, temperature, applied voltage, or the source of copper ions. For those of us with stainless steel kitchen tools, very little maintenance is required to ensure that our pots and pans remain in operable condition. Unlike cast iron or carbon steel cookware, the alloy addition of chromium provides excellent corrosion protection, which allows chefs to cook with acidic foods and leave their pans to soak, worry-free. One precaution that should be taken with stainless steel cookware is to avoid leaving it empty on a heating element. If this precaution is not taken, the metal will be heated to high temperatures, forming multicolored splotches on the surface of the steel. This phenomenon is known as heat tinting and can occur on any stainless steel object heated to sufficient temperatures, which is why it's commonly reported by welders. For this demo, we will need stainless steel washers, pliers or a soldering hand, and a heat source. A stovetop or a candle work well. The procedure for this demo is quite simple. The washer is placed on a heating element or held above a candle using either pliers or a soldering hand, and left until the desired color is attained. The washer is then removed from the heat and allowed to cool. As the name suggests, heat tint occurs when the surface of stainless steel changes color when heat is applied. More accurately, the oxide layer on the surface of the stainless steel thickens, promoted by the applied heat. Chromium is drawn to the surface of the metal, making it richer at the expense of the layers underneath, which could lead to inadequate corrosion protection in some applications. The colors formed are similar to temper colors and are created by a light interference effect. Optical path length differences are the cause of this effect, as light is reflected between the oxide metal interface and the surface of the oxide film, resulting in a characteristic array of heat tint colors. Typically, the color of heat tint can be compared with charts to develop a rough thermal history of the metal, but because these colors vary in shade depending on the thickness of the oxide layer, it is theoretically possible to crudely estimate the thickness of the film as well. When light reflected off the oxide metal interface is in phase with the light reflected off the oxide film, the resultant wave is the sum of the amplitudes. This is constructive interference. If the two reflected waves are out of phase, then their amplitudes cancel each other out. This is destructive interference. When a light of wavelength lambda is reflected from the oxide metal interface, it is eliminated by destructive interference if the thickness of the oxide is 0.25 times lambda. This is because the reflected beam will then have a total optical path length of 0.5 lambda, resulting in light out of phase with that which is reflected off the oxide film, thus leading to destructive interference. If the thickness of the oxide is 0.5 lambda, then the reflected beam will have a total optical length of lambda and be in phase, resulting in constructive interference. Blue light has a wavelength somewhere around 450 nanometers, and red light has a wavelength somewhere around 720 nanometers. If we shine a white light on the washer and a spot appears as a vivid blue, we can infer that the blue light is in phase and the other colors are slightly to completely out of phase, meaning that the oxide layer is likely somewhere between 180 to 225 nanometers thick. In this demo, we explored the oxidation of stainless steel and the colors induced by the creation of an oxide film. Using the color of this film, we estimated approximate thickness of the film itself. An avenue for further exploration may lie with determining the maximum thickness at which the interference effect occurs.